Is that it was a Monday test instead of today.
Yes.
So was 35?
Yeah, we were today.
You're doing what?
Because we're moving points in each class.
You're losing points in each class?
Yeah, like on the test scores. Not you, for anatomy. Yeah.
I wasn't thinking she was calling me weird. Nerd maybe, but not weird. Wait till I come with my bow tie. I have a number of those. Yep, got those too. You haven't seen all those yet. I like fedoras. I have to do something to cover this when I'm outside, otherwise I get burnt.
But what if we got 42?
Exactly. That's what might happen
There you go.
Let me pull this girl.
We're back to backing material. Again. That backing material is that item that sits right behind the crystal. The backing material kind of does two different functions. One, it stops the ringing. The second one is made up of a type of material that stops the transmission of sound from going back and forth. You will, later on when we get into artifacts, hear a term called reverberation, where it's bouncing back and forth between these two things. And that's what the backing material also does. It stops the reverberation from the back side of the transducer crystal. Otherwise, you get more artifacts in it. You don't like artifacts, do we? No. We only want to create things that are real, not things that are fake. Okay. Use those rings dramatically, but reduces the time. So instead of having 5 or 6 pulses, it'll have two or three or 2. It decreases the number of pulses in each transmission because it causes a thump. The only thing that doesn't is what? What continually rings? Continuous wave transducers. Because they're constantly sending and constantly receiving because they have 2 crystals.
Like therapeutic ultrasound.
Yes, but that's only sending. Therapeutic just sends.
So it decreases the number of pulses
In each
in this transmission.
correct. And for the pulse transmission, that series of pulses is diminished when you put it behind, so it stops it. It's like allowing your crystal to ring a teeny bit and then putting your finger on it.
Can you see that one time decreases the number of pulses?
In each transmission,
Thank you.
or in each pulse transmission. Acoustically similar. The reason the vacuum material has to be acoustically similar to the crystal impedance, it prevents that back and forth. Because the crystal doesn't know you want it to go that way. It's going to go that way too when it's sending the sound. If it's similar, it's not going to create that reverberation that's going back and forth. It'll have the same sound into it, so it doesn't create the back and forth motion. 3 factors. The different factors that vacuum material does that decreases sensitivity. Why? Remember when you hear the ringing, you put your finger on it? Well, when the sound comes back and hits it, it also puts a finger on the ringing that it comes back to, so it's not as sensitive to a low frequency. That's why you remember I turned on that thing and I played with it just a teeny bit and waved it, you could hear the sound? That's a continuous wave. That had no vacuum material. That's why you could feel that. Sometimes you can even blow on it and you can feel that.
Is that for when you're doing veins and arteries?
CW, yes.
That's a continuous.
That's one of the methods. You're also going to learn eventually pulse wave. Pulse wave is a whole other entity. That's I think chapter 18 or 19. It'll probably be like 2 weeks on it, if not more. Pulse wave you can also use. But, for doing segmental pressures or a non-invasive testing, we use that and you can hear it. You heard my artery, remember? Mm-hmm. Just by listening to it, you can tell if there's something wrong with it, a stenosis or an issue. going with it. The other thing that it does, the bandwidth. Is it a wide bandwidth or a narrow bandwidth? And in the book, if you look at it, continuous wave is extremely narrow. That means it's emitting almost all of the frequencies at the same one that you have it set at. So if it's a 5 megahertz, almost the entire band is pure 5-wave megahertz transmission. And ultrasound, it's a little different. Matter of fact, if you read the literature on these probes, it says broad bandwidth. That's why you can change your frequency on the transducers electronically up here. You can turn the dial and change to a different frequency because it'll have a bandwidth like this, and you're just selecting across that the different frequencies in the bandwidth. So your bandwidth may be anywhere from, let's just pick it up. What does it say? 1 to 5 megahertz. That's the bandwidth. As to where one of those probes will be 5 megahertz only. This one will transmit at 1 to 5 megahertz by selecting the dial on here.
When they talk about in the book, they switch it when they talk about the range of.
What do you mean by switch it?
Like they say frequencies ranging from 1 to 5 and a bandwidth 5 to 1 or 4. Does that matter?
If you look at doing it, the frequencies you may want may be closer to the center than what you're doing, but the bandwidth may extend a little further, but you're skewing that data out and cutting off the trailers at both ends, is what you're doing with it. So these frequencies at the lower and higher end, what page is that?
118.
On page 118, you look at the book on 118, you'll see what it's looking. The really wide bell-shaped curve, you don't want the two things at the furthest end because you're not going to be able to get very much out of it. You cut off those trailer ends and get more of the center portion. And that's what probably they're talking about when they're dealing with it. And the one that's really steep spike is the continuous wave. The really high spike up. Is it right? Mm-hmm. Yeah, that's continuous wave. It's almost entirely the same transmitted frequency as the electrical pulse you're sending to. So if I have a 5 megahertz transducer, continuous wave, I'm sending the electrical pulses to it at 5 megahertz. So it transmits at what it receives. Here's the last thing, low quality factor. Low quality factor is just a percentage, and we're going to get into each one of these things. You have a high quality factor for the continuous wave, but a low quality factor for the pulse wave. Here's your sensitivity. Inability to convert weak or low signals into meaningful signals. That's what the decreased sensitivity does. Some of the things that we can do is electronically enhance it to try to make up for that. Here's the key. While it reduces the vibration during transmission, it also reduces the vibration on reception. So it's not as sensitive for those low levels that are coming back. It's not vibrating very well. So it's not able to create the signals as it goes back into the electrical pulse. Which one is that? Reverse piezoelectric effect to the piezoelectric effect. With sound hitting the transducer, creating an electrical pulse. Okay. Wide bandwidth, defined as a range between the highest and lowest frequencies in a pulse. To be narrow, the crystal must resonate. Do we all understand what resonate means? Anybody not know what resonate? When I click a crystal and it's ringing, it's resonating with that sound. Or who did the trick? You wet your finger and you put your finger around the top of it and you irritate your brothers or sisters when they're young? I used to do that stuff, that's why. Just what little brothers do, irritate their older siblings. That resonates in a certain frequency.
So resonating is
Resonating creates a narrow frequency. It resonates. In order for it not to, you have to have the backbeat. Our imaging probes do not resonate. The echocardiography people actually have a transducer they call a PDOF probe, which is a CW probe also they use on a heart. And I was going to show you that. But next week I'll bring my toys. Backing material stops the resonation so it's not humming loudly, it just clicks, creating a shorter pulse duration.
Wasn't that question on our test?
No, not in that fashion.
It was similar to.
It was close, but not quite.
It was like treating less or something less.
Here's part of what this is. This short clicking creates the broad bandwidth. When I first started and they had real-time imaging, they tried to do a narrow bandwidth for ultrasound imaging. Till they realized people weren't buying many transducers because they couldn't afford them. So you'd have a 2 megahertz, a 3 megahertz, a 5 megahertz, all these different ones. And of course, we know how much they cost, right? Back then it was cheaper. It was only like $2,000 instead of $10,000. But they've discovered they can make it wider and have one probe that does more things. That had an advantage for a couple of things. The first one is people are lazy. They're not going to unplug this transducer, plug another transducer in just because it gives them a better image quality. They don't want to do that. They want to be done, gone, and out. People are more apt to turn a dial or flip a switch to change the frequency to get a better quality image. And when you get out in the real world, you'd be surprised how often people don't even do that. And I would implore all of you to change your frequencies to see what you can get better. Up, down, lower. I have people routinely going from a 5 megahertz, having it at the primary 5 on the left lobe when it's superficial. They get off to the right lobe, they still have the 5 megahertz, but it's too deep and they can't get good imaging. Is that a question or just stretch?
You're just stretching.
You trying to stay awake? Is that what it is? She smirks and the answer is yes. Short pulses create broad bandwidths. Here's right out of your book again. Now, I'll give you a real big hint. See that? That shows up on your boards in my test questions. See this image?
Yeah.
Narrow bandwidth
That's a
comes
nice
from
question.
what type of transducer? Continuous wave. Broad bandwidth comes with pulse wave. That image will show up, or a semblance from that image will show up on a lot of tests, including mine. Actually, I think that was one of them, wasn't it?
Yes.
Yes. It showed up with the extra points because it was a few slides ahead. And by the way, it may show up on your quiz and or test. It may not show up on the quiz. Just because I already did it. What?
Have it again. I want to get it right.
Quiz and or the next test.
Oh, God.
No, you're not having a test.
Can we have it again?
Broad bandwidth is what?
Broad bandwidth is there because of the backing material that
No,
stops.
I know, but you said it was. one of
This,
them is
see, this
continuous.
wide bandwidth could be a broad bandwidth.
But,
Both turn. Go ahead.
no, but you said broad bandwidth.
The pulse wave.
Okay, now I understand what you're asking. It's pulse wave. The narrow bandwidth, which is a primary of a single frequency, is with continuous wave. Hmm?
Yeah.
I'm warning, something will show up,
Can
at
we make
least
that 30
verbally,
questions?
written, or with the image. Here's your quality factor. It's a mathematical equation related to bandwidth.
We need another question.
Look at it. You don't have to calculate it, but what you have to know is it's main frequency divided by bandwidth is quality factor.